Our planet's map is a temporary snapshot in a 4 billion-year-old dance. Beneath your feet, the ground is part of a slow-motion puzzle that has assembled and shattered entire worlds. These are supercontinents, and their hidden cycle is the most important story our planet has to tell. By the end of this journey, you will understand the secret rhythm that has shaped everything from the air we breathe to the very course of life. We will uncover why continents inevitably clump together only to be torn apart, and what force could possibly be powerful enough to rip a planet in half. What does it feel like to look at the ground and see a fleeting moment in an epic, billion-year journey? That jigsaw puzzle beneath our feet is in constant, deliberate motion. The pieces of this puzzle are tectonic plates, massive slabs of Earth's rigid outer layer, all floating on a hotter, softer layer of rock below. This entire system is driven by a fire deep within the planet. The intense heat left over from Earth's formation and from radioactive decay creates enormous convection currents in the mantle, the vast layer of rock between the core and the crust. Think of it like a pot of thick soup simmering on a stove. The hot soup rises from the bottom, spreads out as it cools near the surface, and then sinks back down again to be reheated. On a planetary scale, this slow, churning motion acts like a colossal conveyor belt, dragging the tectonic plates along for the ride. Where these plates pull apart from one another, new crust is born at volcanic ridges on the ocean floor. Where they collide, one plate might dive beneath another in a process called subduction, creating deep ocean trenches and volcanic mountain chains. And where they simply grind past each other, we get earthquakes. This endless, rhythmic dance of creation and destruction is the engine of our living planet. From this seemingly chaotic motion, a grand and predictable pattern emerges, the supercontinent cycle. It is the planet's slow, steady heartbeat. Continents carried on these conveyor belts are destined to converge. They slowly, inexorably gather together, welding into a single colossal landmass. But that very assembly contains the seeds of its own destruction. A supercontinent acts like a thick blanket, trapping the Earth's internal heat. That built-up heat eventually forces the landmass to crack and rupture from within, sending the continents on a new journey apart, only to be drawn together once more in a future epoch. This cycle of assembly and breakup has repeated itself over and over across the deep history of our world. It is the hidden logic behind the rise and fall of 20 different supercontinents. So where did this epic story begin? We must travel back to the very dawn of the planet itself. Deep within the ancient rocks of South Africa and Western Australia lies the ghost of a world that no longer exists. These two distant lands, now separated by vast oceans, share a geological memory so precise it could only mean one thing. They were once part of the same body, a primordial continent known as Vaalbara. Formed between 3.6 and 3.1 billion years ago, Vaalbara was Earth's first great experiment in continental assembly. The planet was a vastly different place then. A young world with a hotter mantle and a thinner crust, its skies filled with volcanic gases. Vaalbara was not the sprawling supercontinent we might picture today. It was more of a clustered archipelago of the earliest land, built from cratons. These cratons are the ancient, unyielding hearts of continents, the foundational blocks upon which everything else was later built. The evidence for their union is stunningly clear. Geologists have found identical sequences of rock, layer after layer, in both South Africa's Kopval Craton and Western Australia's Pilbara Craton. It is as if someone tore a page from a book and placed one half on each side of the world. The magnetic minerals locked within these rocks tell the same story. their frozen orientations proving these lands were once neighbors. Vaalbara represents the very cradle of continents, the moment our planet first began to stitch together permanent land from the chaos of its youth. Its eventual fragmentation was not an end but a beginning. The dispersal of these first continental seeds set the blueprint for everything that would follow, proving that the great tectonic dance had already begun. From the scattered fragments of Vaalbara, a new and far more resilient land began to take shape. This was a continent that formed roughly 3 billion years ago and would become the single most enduring piece of real estate our planet has ever known. While not a sprawling supercontinent in the grandest sense, was something perhaps more profound, a hardy nucleus of ancient rock that refused to die. Its story is not one of dramatic assembly and shattering, but of quiet, monumental persistence. The cratons that made up pieces of what are now Madagascar, India, and Australia, welded together and then stayed that way, surviving for an almost unimaginable length of time. Think of not as a temporary empire, but as a foundational stone, a piece of the original world that simply would not be recycled back into the Mantle's fiery depths. While other landmasses were born and consumed in the relentless tectonic mill, endured. Geologists see it as the ultimate survivor, a key to understanding how continental crust gains the strength to become permanent. What is the secret to its incredible longevity? The rocks themselves hold the answer. They are less dense, more buoyant, and more chemically evolved than the heavy basalt of the ocean floor, allowing them to float on the mantle like an unsinkable raft. This resilience meant that did not just exist, it accumulated. It became a stable core, a seed crystal around which later and larger supercontinents would inevitably grow. Its legacy is literally the ground beneath our feet in many parts of the world, a silent testament to a world that was, and a foundation for everything that was yet to be built. But the story of is one of quiet survival, not global domination. The first true supercontinent to command a vast portion of the planet was Kenorland. Formed 2.7 billion years ago, this was a world alien to our own. Its skies were thick with methane and carbon dioxide, and its sprawling landmass was surrounded by vast, shallow seas. Kenorland was a giant of the Archean era, one of the first times Earth scattered continental fragments welded together into a single, colossal entity. Its very creation marked a major turning point, a period of intense crustal growth where the planet's skin finally began to stabilize into something permanent. We know of Kenorland's existence from a geological fingerprint scattered across the modern globe. The same ancient rock formations, the same magnetic signatures, are found in the heart of North America, the wilds of Scandinavia, and the plains of South Africa. These lands were once neighbors locked together in this primordial giant, yet Kenorland's most profound legacy was not its assembly, but its death. Its breakup may have plunged the entire planet into its first ice age, the Huronian glaciation. How could a continent breaking apart freeze the world? As Kenorland fractured, it created thousands of miles of new coastline. This fresh, light-colored rock reflected more of the sun's heat back into space, a process known as increasing the planet's albedo. At the same time, the changing ocean currents could no longer distribute warmth evenly across the globe. The result was a runaway cooling effect that may have encased the young Earth in ice for millions of years. This reveals a fundamental truth of the supercontinent cycle. The slow dance of land is not just a geological process, it is the primary driver of our climate. The fragmentation of Kenorland was not an end but a necessary reorganization. Its dispersed fragments became the building blocks for the next, even greater, amalgamation. The cycle was turning, and a new world was already taking shape in the depths of time. The quiet, icy world left in Kenorland's wake did not last forever. Deep below, the Mantle's relentless churning continued, its current slowly gathering the scattered continental fragments once more. This time, the result was a landmass of staggering proportions. Roughly 1.8 billion years ago, the continents converged to form Columbia, a supercontinent so vast it may have been the first to truly encircle the planet. Also called Nuna, this was the Paleoproterozoic Unifier, a single, colossal entity where nearly all the world's land was welded together. Picture a world with one sprawling supercontinent stretching from pole to pole, its interior a dry, mountainous desert far from any sea. The assembly of Columbia was a tectonic event of unimaginable force, a series of monumental collisions that crushed entire continental blocks together. These impacts forged towering mountain belts, the Himalayas of their day, whose worn-down roots are still visible in the ancient cores of North America, Scandinavia, and Siberia. How do we even know this ancient world existed? The evidence is written in stone. Geologists have matched the precise patterns of these aged mountain belts across oceans, like finding two pieces of a torn map. Paleomagnetic data, the fossilized compass needles locked inside the rock, confirm that these now separate lands were once aligned as neighbors. Columbia represents a pivotal moment, a time when plate tectonics began operating in a rhythm we would recognize today. Its formation stabilized the continents and likely triggered profound changes in the atmosphere and oceans, setting the stage for the next great leap in the story of life. But like all supercontinents, Columbia carried the cause of its own demise. Its immense bulk acted as a lid, trapping the Earth's internal heat until the pressure became too great. The breakup was not a sudden explosion, but a slow, inevitable rupture. Fissures opened across the giant landmass, allowing new ocean waters to rush in and begin the long process of separation. This gradual fragmentation created fresh coastlines and new, shallow seas, dispersing the continents on a course that would eventually lead them to their next great rendezvous. The cycle was not broken, it was simply turning its page. The planet's crust, still cooling from the breakup of Columbia, was not destined to remain scattered for long. A new and even more formidable giant was gathering its strength. Rodinia, the motherland, assembled between 1.3 and 0.9 billion years ago, would become the most iconic supercontinent of the Precambrian world. This was a true behemoth, a sprawling, rugged landmass located largely in the southern hemisphere, utterly barren and silent under a thin atmosphere. Its formation was driven by a colossal global mountain-building event known as the Grenville orogeny. The evidence of this titanic crunch is still visible today, with the eroded roots of these ancient mountains found in the hearts of North America, Greenland, Scandinavia, and even Australia. These shared geological scars are the undeniable proof that these lands were once fused together in this primordial union. The very shape of Rodinia is a fascinating puzzle for geologists. Some of the most compelling models suggest it was not a solid mass, but had a unique structure, perhaps resembling a massive donut with a great interior sea at its center. This configuration would have had profound consequences for its climate and its ultimate fate. For nearly 300 million years, Rodinia sat like a vast, inert lid on the planet. But the Earth's internal heat does not tolerate such stagnation. That trapped energy had to go somewhere. Starting around 750 million years ago, Rodinia began to rupture from within. Rift valleys, vast wounds in the continental crust, tore across the supercontinent, allowing new ocean waters to flood in and begin the process of separation. This breakup was not merely a geological event, it was a climatic cataclysm. As the continent fractured, it exposed vast expanses of fresh, dark volcanic rock along the new coastlines. These rocks were exceptionally good at absorbing the sun's heat, potentially triggering a runaway greenhouse effect that warmed the oceans and atmosphere. But in a dramatic twist, this warming may have supercharged the global water cycle, leading to increased rainfall that scrubbed carbon dioxide, a crucial greenhouse gas, out of the atmosphere. With the planet's natural blanket suddenly thinned, global temperatures plummeted. The result may have been the most extreme climate events in Earth's history, the Snowball Earth episodes, where the entire planet, from the poles to the equator, became encased in a thick shell of ice. The shattering of Rodinia did not just rearrange the map, it nearly ended the world, scattering its continental children into a frozen, almost lifeless void. Yet from this icy brink, a new opportunity for life would eventually emerge. From the frozen silence that followed Rodinia, a new world began to stir. The scattered continents, driven by the Earth's deep currents, began a slow drift toward the South Pole. Their brief convergence created Pannotia, a supercontinent that was more of a hasty gathering than a permanent union. Formed between 633 and 573 million years ago, Pannotia was a loose assembly, a collection of landmasses clustered around the southern polar region. It was not the tight, solid giant that Rodinia had been, but rather a transitional configuration, a fleeting moment of continental connection. The major players in this brief assemblage were the ancient cores of Gondwana and Laurasia, the future foundations of the southern continents and North America. Pannosia's true importance lies not in its size or its longevity, but in its exquisite timing. It existed during the Ediacaran period, a pivotal chapter in Earth's history when the first complex, multicellular life forms began to appear in the oceans. These were soft-bodied, strange creatures unlike anything that exists today, and they inhabited a world dominated by this transient southern landmass. But Pannotia was not built to last. Its rapid fragmentation, beginning around 540 million years ago, was a geological event with profound biological consequences. As the supercontinent broke apart, it created an incredible network of new coastlines, warm, shallow seas, and isolated marine habitats. These new environments became evolutionary crucibles, places where life could experiment and diversify without intense competition. The sudden availability of these ecological niches is widely believed to be a primary trigger for the Cambrian explosion, that breathtakingly rapid burst of evolutionary innovation where almost every major animal body plan we know today first appeared in the fossil record. The breaking apart of a continent did not just change the map, it directly authored the next chapter in the story of life itself. The logic of the supercontinent cycle had now proven its power over biology, setting the stage for the most famous landmass in Earth's long history. The stage was now set for a titan. From the fleeting assembly of Pannotia, a new and far more enduring landmass began to coalesce. This was Gondwana, the great southern supercontinent. While some debate its classification as a true global supercontinent, its sheer immensity and incredible longevity make it a cornerstone of our planet's story. Gondwana began forming around 550 million years ago, gathering the southern fragments of the world into a single, colossal entity. Imagine a land where the future continents of South America, Africa, Arabia, Madagascar, India, Australia, and Antarctica were all locked together as one. This was not a brief encounter, but a marriage of continents that would last for hundreds of millions of years. Gondwana was a stable, persistent world, a witness to epic transformations. It existed through the age of ancient fish, saw the first forests rise, watched the dinosaurs conquer the land, and felt the first stirrings of mammals in the undergrowth. The proof of its unity is etched into the very fabric of the southern continents. Geologists find the same fossilized plants, like the distinctive Glossopteris flora, in rocks from South America to Australia to Antarctica. These ancient seeds could not have crossed vast oceans. They prove these lands were once a continuous garden. The rock layers themselves are identical, a perfect geological fingerprint that matches across thousands of miles of open water. But even this stable giant was not immune to the planet's deep rhythms. Its breakup began slowly during the Jurassic period, a gradual, protracted rifting that tore the supercontinent apart over millions of years. As the land fragmented, the South Atlantic Ocean was born, slowly unzipping the seam between South America and Africa. The Indian Ocean began to form, sending the Indian subcontinent on a long, lonely voyage northward. This was not a violent shattering, but a slow, inexorable divorce that gave the world the southern continents we recognize on our maps today. The story of Gondwana teaches us that the supercontinent cycle is not always a story of rapid cataclysm. It is also a tale of profound stability and gradual change, a reminder that the ground beneath us holds the memory of a world that was once profoundly and permanently connected. While Gondwana held the southern hemisphere in its ancient grip, a rival landmass was rising in the north. Laurasia, often called the Old Red Sandstone Continent, assembled during the Devonian period some 400 million years ago. It was born from a monumental tectonic handshake, the slow, grinding collision of Laurentia, the core of North America, with Baltica, the heart of Europe. This new continent straddled the equator, a world of stark contrasts. Its vast interior was a scorching, arid desert, a landscape where the relentless sun baked the distinctive red sediments that give this continent its name. These old red sandstone layers, found today from the British Isles to North America, are more than just colorful rock. They are the pages of a dusty diary, preserving the bones of the first vertebrates to truly conquer the land. This was the world of early amphibians, creatures navigating the waterways of a harsh interior, and of sprawling reef systems that teemed with life in the shallow seas along its coasts. The very creation of Laurasia forged a mountain range of epic proportions, the Caledonian Appalachian chain. The worn-down roots of these once towering peaks are a permanent testament to the colossal force of that collision, a geological spine that still connects Norway to Scotland and runs the length of the eastern United States. Laurasia itself was not a global supercontinent, but its formation was a critical, deliberate step in the planet's grand plan. It was a major continental amalgamation, a crucial building block. Its existence proves that the journey to a supercontinent is not a single, sudden event, but a meticulous process of assembly. Smaller landmasses weld together into larger provinces, which then await their final, world-altering union. With Laurasia now solid in the north and the immense bulk of Gondwana stable in the south, the stage was set. The two great landmasses of the world were now poised for a collision that would shake the planet to its core. The final and most famous of Earth's great unions was now at hand. Pangea, the all-Earth supercontinent, assembled its colossal form between 335 and 250 million years ago. This was the last time in our planet's history that every major landmass was welded into a single, universal entity. Picture a giant C-shaped continent, a sprawling world island that stretched from pole to pole. It was surrounded by a single, planet-wide ocean known as Panthalassa, with a great indentation on its eastern side called the Tethys Sea, a warm, shallow cradle of life. The birth of Pangea was the ultimate tectonic collision, the slow, grinding convergence of the southern giant Gondwana with the northern continent of Laurasia. The force of this impact was so immense that it thrust up the central Pangean Mountains, a Himalayan scale range whose eroded roots now form the Appalachian Mountains of North America and the Caledonian Mountains of Europe. Life on Pangea experienced a world of extremes. The interior of the supercontinent, far from the moderating influence of the ocean, became a sprawling, scorching desert. Daytime temperatures would have been blistering, while nights could plunge into frigid cold. Global weather patterns were completely reconfigured, with monsoon systems raging along its coasts while the heart of the continent baked. How can we be so certain this singular world existed? The proof is written in stone and bone. Identical fossils of land-dwelling reptiles like Cynognathus and the plant Glossopteris are found in South America, Africa, India, and Antarctica. These creatures and plants could never have crossed the oceans that separate these lands today. Their remains are the undeniable evidence that these continents were once a continuous, walkable landscape. Yet, true to the relentless logic of the supercontinent cycle, Pangea's very existence sealed its fate. By acting as a thick, insulating lid, it trapped the Earth's internal heat. Around 175 million years ago, that pent-up energy found its release. A massive rift, a continental wound, began to tear through the supercontinent, starting the long, slow process of separation that created the Atlantic Ocean and set the continents on their current trajectories. This breakup is not a finished event. It is a process that continues today at the speed your fingernails grow, shaping the very map you look at right now. Pangea is the key that unlocks our modern world, the most recent chapter in a story that is far from over. The ground you stand on is still in motion, its journey far from complete. The Atlantic Ocean is slowly but surely widening, pushing the Americas further from Europe and Africa at a pace no faster than a growing fingernail. Yet this very motion contains the blueprint for its own reversal. The same mantle currents that drive the continents apart will one day pull them back together. In roughly 200 to 300 million years, our familiar world map will be utterly unrecognizable. The next great supercontinent, which scientists call Amasia, is predicted to form as the Atlantic stops expanding and begins to close. The Americas will swing eastward, colliding with a merged Europe, Africa, and Asia in a monumental tectonic embrace centered around the North Pole. Picture a world where the Arctic Ocean is a landlocked sea at the heart of a new global giant. But this is not the only possible future. Another compelling model, known as Novopangia, suggests a different fate. In this scenario, the vast Pacific Ocean, not the Atlantic, will be the one to close. Australia and the Americas would drift westward, eventually welding onto Asia's eastern flank. These are not wild guesses. They are scientific forecasts based on meticulously tracking the current drift of the continents and modeling the immense, persistent forces churning within the Earth's mantle. The formation of Amasia would be a climatic and biological upheaval. A landmass clustered at the North Pole would develop a massive ice cap, reflecting sunlight and cooling the entire planet. Sea levels would fall as water was locked up in ice, and the new interior deserts of this supercontinent would be more extreme than anything we know today. Countless species would be driven to extinction by the changing environments, while new evolutionary paths would open in the isolated habitats created by the collision. This forward vision reveals the true nature of the supercontinent cycle. It is not a relic of the deep past but an active, ongoing process. We are living in the dispersal phase that followed Pangea's breakup, a single chapter in a story that has been repeating for billions of years. To contemplate Amasia is to stretch our minds across a timescale that dwarfs human history, a humbling reminder that the planet's greatest transformations are still to come. The secret rhythm that governs our planet's face has a name, the Wilson cycle. It is the fundamental pulse behind the epic dance of supercontinents, a pattern of ocean basins opening and closing over hundreds of millions of years. This cycle, named for the visionary geologist J. Tuzo Wilson, reveals that every ocean has a lifespan. It is born, it matures, and it dies. Think of the Atlantic Ocean today. It began as a mere crack, a continental rift tearing through the heart of Pangea. That crack widened, filled with water, and grew into the vast basin that separates the Americas from Europe and Africa. But this expansion is not eternal. The same forces that created it will one day reverse. New subduction zones will form, and the ocean floor will begin to plunge back into the mantle, slowly, inexorably closing the Atlantic until the continents meet once more in a colossal embrace. This is the hidden logic, a perpetual balance between creation and destruction. At mid-ocean ridges, the Earth's crust is born fresh from the mantle, pushing the plates apart. At deep sea trenches, that very same crust is consumed, dragged back into the planet's fiery interior. The entire supercontinent cycle is an expression of this deeper, more fundamental rhythm. When a supercontinent like Pangea sits like a massive lid, it traps immense heat. This heat eventually forces the land to rupture, creating a new ocean basin. But as that new ocean widens, the cold, dense, old crust on the opposite side of the planet becomes unstable. It begins to sink, initiating subduction. These subduction zones act like anchors, their relentless pull eventually drawing the continents back together. The assembly of a new supercontinent is not a random accident. It is the direct result of oceans closing, of continents being steered by these sinking slabs of cold rock deep within the mantle. Yet this is not a simple, perfect clockwork. The Wilson cycle provides the essential framework, but the reality is a complex, messy interplay of forces. The Earth's internal heat is slowly declining, changing the vigor of mantle convection over billions of years. The continents themselves are not passive rafts. Their inherent strength, their buoyancy, and their deep roots all resist the mantle's pull, adding friction and unpredictability to the process. The logic is clear, but its execution is a planetary drama of competing powers, a story written in the slow, grinding motion of rock. This planetary thermostat is powered by the relentless churning of the mantle. Deep beneath the rigid plates we live on, the Earth's mantle behaves like an incredibly slow-moving fluid, a vast ocean of solid rock that flows over millions of years. The heat from the planet's core and from radioactive decay drives this motion, creating massive convection currents. Picture a pot of thick soup simmering on a stove. The hottest soup at the bottom rises toward the surface, while the cooler soup at the top sinks back down to be reheated. On a planetary scale, this is the engine of plate tectonics. But what happens when you place a lid on that pot? A supercontinent acts as that very lid, a giant insulating blanket smothering the Earth's surface. The continents are made of rock that is less efficient at conducting heat than the thinner oceanic crust. When they are all clumped together, they trap the planet's internal heat, causing the mantle directly beneath to grow progressively hotter. This buildup of thermal energy cannot be contained forever. It eventually finds a release in the form of superplumes, colossal upwellings of superheated rock that rise from the deep mantle. These are not gentle swells, but planet-scale pillars of heat that press forcefully against the underside of the supercontinent. The lithosphere, the rigid outer shell, begins to dome upwards and stretch thin above these plumes, like a sheet of plastic held over a powerful flame. The continental crust, weakened from below, begins to crack. Vast rift valleys tear across the landscape, the first mortal wounds in the supercontinent's bulk. This entire process is a perfect feedback loop, a self-regulating planetary system. Continental assembly inevitably leads to insulation. Insulation forces the mantle to overheat. That overheating generates the superplumes that literally push the continent apart. The evidence for this is written in fire across the globe. When Pangea began to rupture, one of the most enormous volcanic events in Earth's history erupted across the newly forming Atlantic. The Central Atlantic magmatic province left behind a staggering volume of solidified lava, a testament to the superheated plume that fractured the supercontinent from within. This is the hidden logic that governs the cycle. The Earth possesses its own built-in thermostat, a deep-seated thermal regulation system that ensures no single landmass can dominate the planet forever. It is a cycle of pressure and release, of gathering heat and explosive renewal, written in the very rock we walk upon. The precise spot where a supercontinent comes to rest on the globe acts as a master switch for its entire future. Its location and orientation are not a matter of chance but a critical variable in the planetary equation. Geologists have identified two fundamental modes for how these giants assemble. The first is extraversion, where the continents turn inward to close an interior sea. Pangea is the classic example, forming as the ancient Iapetus Ocean vanished and the landmasses sealed shut the Tethys Sea on their eastern flank. The second mode is introversion, a process where the continents reverse course to consume the vast exterior ocean that surrounded them. Imagine the future closing of the Pacific Ocean, pulling the Americas backward into Asia to form the next supercontinent. This choice of path, whether the continents fold inward or sweep outward, dictates which oceans live and which oceans die, but the logic goes even deeper, tied to the very spin of the planet. A supercontinent centered over the equator, like Pangea, experiences significant rotational forces. The Earth's spin creates a subtle but persistent flinging effect, a centrifugal push that can influence where the landmass is most likely to rupture. In contrast, a supercontinent centered over a pole, as some models predict for the future Amasia, would experience these forces differently, potentially leading to a more stable, compact configuration. This rotational stress interacts with the trapped heat beneath the supercontinent, guiding the formation of rift valleys and ultimately determining the escape routes for the dispersing fragments. We see this precise geometric control in the breakup of the ancient supercontinent Rodinia. Its unique configuration, possibly a ring-shaped landmass with an interior sea, created specific lines of weakness. When the heat built up, the continent fractured along a predictable pattern, sending its continental pieces drifting on trajectories that were preordained by its original shape and position. This spatial dimension reveals a hidden layer of order. The assembly and breakup of supercontinents are not a chaotic free-for-all. They are a complex geometric dance, a kinematic puzzle where the planet's rotation, the pre-existing web of subduction zones, and the stubborn buoyancy of the continents themselves all conspire to write the next chapter of the map. The confidence we have in these ancient worlds comes not from guesswork, but from reading the planet's own permanent records. One of the most powerful tools for this is paleomagnetism. When volcanic rock erupts and begins to cool, tiny magnetic minerals within it, like miniature compass needles, freeze in place, aligning perfectly with the Earth's magnetic field at that exact moment in deep time. This locks in a precise record of the rock's latitude, capturing its location on the globe as if taking a snapshot. By analyzing these magnetic signatures in ancient rocks from, say, Brazil and Western Africa, scientists can demonstrate that these now separate lands shared the same latitude billions of years ago, proving they were once a single body. This is the invisible thread that stitches continents back together. Another undeniable line of evidence comes from the fossils and the rocks themselves. The discovery of the freshwater reptile Mesosaurus provided a stunning clue. Its fossils are found exclusively in eastern South America and western Africa. This was a small, coastal creature that could never have survived a journey across thousands of miles of open ocean. Its presence on both shores is irrefutable proof that these continents were once connected, its home a single lake or river system that was later torn in two. The very bones of the land tell the same story. Look at a map of the Appalachian Mountains in North America and the Caledonian Mountains in Scotland and Norway. These are not separate ranges, they are the two halves of a single, ancient mountain belt. The colossal suture line formed when their continents collided and then later ripped apart. These diverse clues, from frozen magnetism to shared fossils and matching rock layers, all converge. They are the multiple, independent witnesses that testify to the same incredible story, allowing us to reconstruct the map of a lost world with a certainty that is as solid as the rock we stand on. This profound connection between geology and biology means the ground beneath us is more than just a stage for life. It is the director of the entire play. When continents merge into a single, sprawling supercontinent, they create a world of both opportunity and peril. For the first time, land animals and plants can disperse across thousands of miles of continuous territory. Different species, once separated by oceans, are suddenly thrust into competition. This intense biological pressure can be a powerful furnace for evolutionary innovation, forcing creatures to adapt rapidly or perish. But this new, unified world also has a harsh, sterile heart. The vast interior of a supercontinent, far from the life-giving moisture of the sea, becomes an immense desert. With most of the world's landmass clumped together, the total length of coastline, those rich, shallow, sun-drenched nurseries of marine life, is drastically reduced. This overall loss of habitat variety can actually suppress global biodiversity, creating a world that is vast but surprisingly monotonous. The assembly of a supercontinent, then, often centralizes life only to place it under immense strain. The true explosion of life occurs when the giant shatters. The breakup of a supercontinent is the ultimate catalyst for biological creativity. As a massive landmass fractures, new oceans flood into the rift valleys, physically separating populations of animals and plants. A single species, once roaming a continuous forest, finds itself stranded on two different islands that are slowly drifting apart. Isolated in their new environments with different climates, predators, and food sources, these separated populations begin to evolve in completely independent directions. Over millions of years, they become distinct species, a process known as allopatric speciation. This is the primary engine that has generated the incredible variety of life on Earth, from the unique marsupials of Australia to the lemurs of Madagascar. Their very existence is a direct result of continental divorce, yet this tectonic force is also an agent of destruction. The same superheated mantle plumes that rip continents apart often manifest on the surface as catastrophic volcanic events known as large igneous provinces. These are not single volcanoes, but continent-scale floods of lava that can erupt for thousands of years, pumping unimaginable quantities of gas and ash into the atmosphere. The volcanic gases from the Siberian traps, which erupted as Pangea was fracturing, are widely believed to have triggered the Permian-Triassic extinction, the most severe mass dying in Earth's history. The very same process that creates new species by isolation can also wipe the slate nearly clean with fire. The logic of the supercontinent cycle is therefore written in the fossil record itself, a rhythm of creation and destruction that proves the destiny of every living thing is tied to the slow, relentless pulse of the planet. The slow dance of continents is the ultimate architect of our planet's climate. a force capable of flipping the entire world from a tropical greenhouse into a frozen icehouse. When a supercontinent like Pangea or Rodinia dominates the globe, it fundamentally rewrites the rules of weather. Its vast, singular interior, thousands of miles from any ocean, becomes a land of brutal extremes. Imagine scorching summers and frigid winters, a sprawling desert where the only moisture comes from the occasional, violent storm. This happens because the planet's atmospheric circulation, the great engine of winds that redistributes heat and rain, is completely disrupted by this monolithic landmass. Ocean currents, the other great climate regulator, are also thwarted. With continents clumped together, there are no seaways to allow currents to circulate freely and carry warm water from the equator toward the poles. The planet's ability to moderate its own temperature breaks down, leading to a world of harsh, unpredictable seasons. But the climatic impact of a supercontinent is full of surprising contradictions. While the interior bakes, the very act of assembling the landmass can plunge the world into a deep freeze. A supercontinent centered over a pole, as Pannotia was, becomes a massive, high-altitude platform for ice. Its white surface reflects sunlight back into space, cooling the planet and triggering a positive feedback loop that can encase the globe in ice. This is the icehouse state. Then comes the breakup. As the colossal landmass fractures, new oceans are born. These young seaways are not just empty spaces on a map, they are revolutionary new highways for ocean currents. The most dramatic example is the Drake Passage. When South America finally fully separated from Antarctica around 30 million years ago, it opened an unimpeded channel around the bottom of the world. This allowed the Antarctic Circumpolar Current to form, a relentless, cold river of water that circles Antarctica, effectively isolating it from the warmer waters of the world. This oceanic isolation was a direct primary cause of the permanent ice sheet that blankets the continent today. Yet, the fragmentation of a supercontinent also has a warming effect. All that rifting and tearing of continental crust creates massive volcanic activity, pouring enormous quantities of carbon dioxide into the atmosphere for millions of years. This thickens the planet's natural greenhouse blanket, trapping heat and often creating a global greenhouse period of steamy, tropical temperatures from pole to pole. The supercontinent cycle is therefore the planet's master climate switch, a slow but relentless oscillator between icehouse and greenhouse worlds, proving that the ground beneath our feet holds the thermostat for the entire planet. The grand narrative of supercontinents is built not only on giants like Pangea, but also on a host of shadowy, theoretical lands. Filling out the full list of 20 requires us to venture into the realm of the hypothetical, where the evidence is more subtle and the maps are drawn in dotted lines. These are the protocontinents and partial assemblies, names like Superia and Sclavia. These are not single landmasses in the traditional sense, but rather the proposed clustering of the very first cratons in the Archean world, over 2.5 billion years ago. They represent the earliest whispers of order emerging from the planetary chaos, the first tentative groupings of those unsinkable rafts of ancient crust before the first true supercontinents like Kenorland took shape. Their existence is inferred from the scattered distribution of these primordial cratons, a ghostly pattern suggesting they were once neighbors in a long-vanished configuration. Another key piece of this ancient puzzle is Atlantica. This was not a global supercontinent, but a significant Paleoproterozoic landmass that brought together the ancient cores of what is now Eastern South America and Western Africa. The São Francisco and Congo cratons were once fused, a union that predated and later contributed to the assembly of the colossal supercontinent Columbia. Why does this matter? Because it reveals the true, granular nature of the supercontinent cycle. the journey is not a simple, clean switch from one global giant to the next. It is a continuous, messy process of smaller continental blocks merging into provinces, those provinces then colliding to form a supercontinent, only to fragment back into a new set of constituent parts. Each of these theoretical assemblies, from Superia to Atlantica, is a crucial piece of the grand kinematic puzzle. They help us refine our models of how crustal blocks move and weld together across the eons. Their debated existence is a powerful reminder that the geological record is inherently fragmentary, a book with most of its pages missing. Every proposed supercontinent, whether firmly proven or still a subject of scientific discussion, adds another vital piece to our understanding of Earth's deepest, most dynamic history, proving that the planet's story is still being deciphered from the stones. The maps we draw of these ancient worlds are not set in stone, for the stones themselves tell a story that is constantly being reinterpreted. This search for our planet's past is a living, breathing science filled with vigorous debates that challenge our most fundamental assumptions. Take the very first supercontinents, Vaalbara and Kenorland. Some researchers question if Kenorland was truly a single, cohesive entity, or if it was instead a looser archipelago of smaller landmasses that were merely neighbors, not a unified giant. The evidence is fragmentary, scattered across billions of years, and new data can suddenly tilt the scales of a long-held theory. The puzzle of Rodinia is even more contentious. Multiple competing models exist, each proposing a radically different arrangement of the continental blocks. One model might place Australia against Western North America, while another positions it alongside southern China. These are not minor disagreements, they represent fundamentally different visions of a lost world. Even the definition of a supercontinent is up for debate. Must it include virtually all of the planet's land, like Pangea did, or can a massive, long-lasting assembly like Gondwana earn the title? This question is more than semantic. It strikes at the heart of the cycle's logic and its impact on global climate and evolution. These scientific controversies are not a sign of weakness, but the very engine of discovery. They are driven by new high-precision dating techniques, advanced computer simulations of mantle flow, and fresh interpretations of magnetic data locked in ancient rocks. Each debate forces a deeper look, a more creative connection, pushing our understanding of the planet's hidden rhythm beyond what we thought was possible. The ground beneath us holds many secrets, and its greatest mysteries are still being unearthed, one contested stone at a time. The story of 20 supercontinents is not a collection of separate tales, but a single, epic narrative written in the language of planetary physics. This grand unified theory weaves together every giant, from the primordial Vaalbara to the future Amasia, revealing a multi-layered logic that is both elegant and profound. At its most fundamental level, we have the Wilson cycle, the perpetual opening and closing of ocean basins that acts as the engine's pistons. This rhythm is powered by the deep churn of Mantle convection, the planet's way of releasing its internal fire. A supercontinent acts as a lid, trapping that heat until it can no longer be contained, forcing the land to rupture and disperse. This entire system is a planetary thermostat, a self-regulating mechanism for managing Earth's internal energy. Yet the process is not a simple metronomic tick-tock. The specific geometry of each supercontinent, its location on the globe, acts as a master control, determining where it will rift and how its fragments will journey across the planet. The cycle itself is evolving. Over 4 billion years, the Earth's interior has steadily cooled. This gradual loss of heat has fundamentally changed the style of plate tectonics. In the planet's fiery youth, the mantle churned with more vigor, likely causing supercontinent cycles to be faster, more chaotic, and perhaps less complete. The assembly and breakup of the earliest giants like Kenorland and Columbia may have been rapid, tumultuous affairs. Later cycles, like the one that meticulously built Pangea, appear more deliberate and regular, a sign of a maturing, cooling planet. This unifying theme transforms our understanding. The supercontinent cycle is not a preordained program, but an emergent property. It is the inevitable consequence of a differentiated planet, a world with a hot core and a mobile, rocky shell, slowly losing its heat into space. This grand process is the planet's way of managing its own energy budget, and in doing so, it becomes the ultimate conductor for the epic symphonies of continental drift, the violent swings between icehouse and greenhouse climates, and the relentless pulse of biological evolution and extinction. All 20 supercontinents are simply different verses in this single, ongoing song of a living, breathing world. Our journey through these 20 ancient worlds reveals a planet in constant, majestic motion, governed by a deep and hidden logic. From the first whispers of Vaalbara to the future prophecy of Amasia, we have traced the fundamental pulse of Earth itself. This relentless cycle of assembly and breakup, driven by the engine of plate tectonics, has done far more than just rearrange the map. It has raised the mountains that catch the rain, carved the oceans that govern our climate, and opened the evolutionary pathways that led to us. Every breath you take, every landscape you admire, bears the indelible mark of this grand planetary rhythm. The familiar map on your wall is not a permanent fact. It is a single frame in a movie billions of years long. The Atlantic is still widening, the Pacific is still closing, and the continents continue their slow, inexorable drift toward their next great collision. We are temporary passengers on a dynamic world, living on a stage whose scenery is perpetually being rebuilt. The planet's entire history is written in the stone beneath our feet, and its next chapter is being forged in the fiery mantle below. To grasp this scale of time and change is to see our world with new eyes, to understand our place within a story far greater than our own. If this journey into the deep past and far future has captivated you, we would love to hear your thoughts in the comments. Share your wonder and subscribe to join us as we continue to explore the profound mysteries of our living planet.